Hello, everyone. A model-assisted approach for finding coding errors in manual coding of open-ended questions. Open-ended questions. This is joint work with Sophie He, my former PhD student. We're talking about open-ended questions, and open-ended questions give text answers. And those text answers are often hand-coded, manually coded, into one of several classes or codes. People make mistakes, and one way of establishing the extent of how correct it is to code a random subset doubly. So it's a double-coded subset to assess the inter-rater reliability. And just in terms of getting the notation, the double-coded subset has n1 observations, and the remainder is single-coded. So the remainder out of the n observations, n minus n1. What is double coding? Well, two coders independently assign a code to a text answer based on a manual that the researcher or investigator has supplied. And they do this independently, and they may disagree. And if they disagree, the disagreement is resolved in one of several ways. So, for example, they might discuss until they agree, or you might get a third coder who casts the deciding vote, or you might get an expert third coder, such as the investigator, him or herself, or somebody else who's an expert, and they decide. The resolved code is called the gold standard, or we call it the gold standard. And it's not like no error could happen in the gold standard, but it's pretty good. And relative to this gold standard, when two coders disagree, then one of them must disagree with the gold standard. And that's what we call a coding error here. So for the double-coded data, the subset, which may be 200, 300 observations, we know where the errors are because we know where the two coders disagreed. So we know most of the errors, let's say it that way. And this is this subset of size n1. Can we identify suspicious codes in the single-coded data? And by suspicious, I mean, what are the single-coded data that are very likely or most likely to lead to a disagreement if they were double-coded? So that is easy on the data that is already double-coded. You just see which one matches, which one doesn't. But it's hard on the majority of the data, which are single-coded. We have two methods to get at this, to find suspicious answers, suspicious codes for the answers. And just to get the naming right here, so we call the coder that codes all the observations coder 1, and the coder that codes only the n1 observations for the double coding coder B. So the first method is labeled predict codes first. What we're doing is we're training a model on coder B's codes. And this outcome, of course, has multiple classes because we're coding typically into more than 2 classes. It could be 8 classes, 10 classes. And then we predict the probability that coder B gets the same code as coder A on the single-coded data, on the remaining observations. And the risk of disagreement is then 1 minus this probability. I have said sort of fairly casually, we train the model on coder B's codes. This assumes that you have translated the text into variables, into n-gram variables, and I'll talk about that for a second. And the model that we actually use is a statistical learning or machine learning model. It supports vector machines, but the method is fairly robust, as we shall see later. Method 2. So method 1 was we predict based on the double-coded data of coda B, the codes from coda B, we predict coda B's codes for the remaining data. In method 2, we predict disagreement directly. So rather than just concentrating on coda B, we say, well, where do we disagree in the training data, in the double-coded training data? So we have a binary outcome, disagree or don't disagree, and then we predict the binary outcome on the remaining single-coded data. Yeah, and so it's not quite clear which of these two methods is going to be better. And let's see, we have some results. So first, this little excursion into n-gram variables. When we have text, we cannot directly run a machine learning model on it, at least not usually. And so I'm using here we're using the n-gram variables to turn text into data, into variables. So for example, no vaccine, all is challenging, challenge. This has the word challenging twice. So we count the occurrence of words. Here we have a 2 there. Then corona doesn't appear. Vaccine shows up once here. And there's a total of 6 words in there. 1, 2, 3, 4, 5, 6. Now, to be fair, challenge doesn't really show up in the same way. There's challenging and there's challenge. We get rid of the capital letters. We get rid of the punctuation here. And then there is a technique called stemming that chops off the ending of words in an attempt to reproduce the root of the word, which is challenge without the ing in there. So we cut off the ing there and the e there. This all happens automatically. I have some software for this. And this way we create variables. Okay, this is not the focus of the talk, so I will just leave it at that. So we are using a method that counts occurrence of words or sequences of words to create variables. Experiments. So we're using fully double-coded data, so we can simulate both procedures and see how they work relative to random selection. All right, and how do we proceed? So we're doing every time 1,000 simulations, which then allows us to also give sort of an empirical confidence intervals of the middle 950 observations. And we first set N1 training observations at random. And these are the N1s that are going to be double-coded, right? Then we choose support vector machines as our training model here. So machine learning model. We tune these support vector machines with a specific split here. Tuning is something that is standard procedure in statistical learning, machine learning, when a regression model is highly flexible to avoid overfitting. So it's a standard procedure here, and there is a parameter in support vector machines that requires tuning. If you are more familiar with logistic regression and linear Gaussian regression, you wouldn't have seen this. So this is for more flexible models. We fit the SVM on the training data, and then depending on the method, we choose N2 observations following method 1 or method 2, the most suspicious observations. And then we compute an evaluation metric, such as the % disagreements or something like that. All right, we have 3 data sets we're working with. And I'm just giving a brief overview here. Patient Joe data is a hypothetical scenario at a doctor's office. And the question that the respondents are asked, what advice would you give Joe, or specifically, what should Joe do? This is categorized into 4 classes, whether the advice reflects proactive behavior, somewhat proactive passive, or counterproductive. Which means go away to the hospital, leave the doctor, basically. Then there is a happiness data. What aspects of your life did you consider when assessing your feeling of happiness? In German, and there are 10 classes. You can see the details. And the democracy data, how content are you all in all with the way democracy functions in Germany? There are 7 different classes. Right? The amount of disagreements here range from 5% in the happiness data to 23% of the patient Joe data. This is the disagreement rate of the double coding because all three data sets are fully double coded. And the number of observations here range from 1,000 to 1,700 in this data sets. Here are some results. We're first only looking at finding 250 suspicious codes. So we had trained it on 250 random codes, and then we select 250 suspicious codes. And because we have done this procedure 1,000 times, we get here the box plots, and not just one observation. There's one panel for each data set, and then we have a different color for each method, where we have method 1, method 2, and then compared to random selection. So we see that the predict codes first method gives the best results, and that it finds the most number of disagreements. The number of disagreements varies widely because some data sets have more disagreements than others. But for the patient Joe data, if we think about, we picked 250 suspicious codes, 150 of them were actual disagreements, meaning errors. That's pretty good, I would say. All right, so to more formally evaluate that, we can look not just as picking exactly 250 suspicious codes, but suspicious codes ranging from what would happen if you pick just 50 or a few to all the way to very many suspicious codes. And then we can evaluate sort of metrics such as recall and recall, which is also called sensitivity. So you're seeing here 1,500 observations because there are 1,500 observations single-coded left over after the first 250 double-coded ones. And that varies by happiness because the data set is slightly smaller, and here democracy is also a bit smaller. And for all three, you see that the predict codes method, the red method here, does best, and that it has the greatest recall. Recall or sensitivity means the number of disagreements or the percent disagreements detected in the N2 answers out of the number of disagreements in the remaining N minus N1 answers. So among all the outstanding errors in the single data, what percentage did we detect? Of course, the more suspicious codes you declare, the more you're going to detect, and you have to settle on somewhere here. Okay, so, and we've seen already that for patient Joe, if we take another 250 observations, that leads to, if we go up this here, to 43% sensitivity, which corresponds to roughly 150 codes on the previous page. This is pretty good. Miracles are not expected, so outside of miracles, pretty good. Precision. The precision among the N2 answers selected refers to the percentage of disagreements found. And that, again, varies by method. And in all cases, the predict codes does best. So I think we have our answers. So I just want to point out this converges towards the percentage of disagreements left in the single-coded data, which is different for the three data sets. This is robust with respect to the choice of support vector machines versus different kernel for support vector machines versus random forest or some other method. So in summary, what did we find? We found that predict codes first identifies 2 to 3 times as many coding errors in the additional text answers, in suspicious answers, as compared to random guessing on average. So we think this procedure is attractive if budget permits additional double coding. When there's a lot of intercoded disagreements, the benefit can also be substantial. This talk is based on this paper here above to appear. There are some other papers related to open-ended questions in this space, coding open-ended questions. If you're wondering how I created the n-gram variables, there's some data software down here in the last paper. Thank you very much for listening.